So up to now, we've been talking about how to query a search index. How do you update a search index when you find new documents, for example? Well, the design of this has been carefully engineered to fit the domain. So text search engines are designed to be query mostly because interactive delete and modification is relatively rare. You can't very easily go to Google and say, please delete this one page from your web index. Right? They're not interested in doing that. What they'll do is periodically in batch, they'll update the web index to reflect the current state of reality. And so these updates are postponed, and nobody really notices when they happen. There's no transactions going on here where someone's like, oh my gosh, my bank account is wrong. That doesn't happen with web search. We don't worry if Google doesn't currently have the particular page. We worry over time, but we might not worry for a single query. And so that means that we can postpone updates. We can have the indexes that we're building kind of be a union of old versions of the database and new versions of the database. And we can merge these old and new indexes in the batch in the background. Now, for those of you who'd like to go learn more, you can read about what's called log structured merge or LSM trees, which are a variation of B trees that account for this kind of batch update over time. In order to install an update into an existing index, you often have to go offline or be locked for a short amount of time. An alternative scheme to that is simply to create a second index, even on a separate machine, which is a copy of the first but with fresh new data. And then when the second index is built, you can simply delete the first index and route queries to the second index, and then use the machine that had the first index to start over again, building yet a new index. So it's quite common in some cases to use this kind of alternation of extra resources to allow the indexes to never be offline. There's just a new one being built in the background at all times, and then a switch over from old to new periodically. And this avoids what we would call concurrency control problems in traditional relational databases. One of the other keys with text search is that because they're query mostly, we can compress the B trees to be search friendly and update unfriendly. So we can create B trees where insertion would be really expensive. And that's okay because we won't insert into these B trees. And they're only used for querying, and we replace them, as I described before, when we want to update them. So that's an option that allows us to customize again to this query mostly workload. And then finally, as we said, we're keeping our postings lists at the bottom of these B trees sorted. That is not something we'd want to do in an index where we're doing dynamic updates. So these are query mostly indexes where we don't update the leaves much, and therefore it's not too expensive to have those postings lists sorted. It happens when we bulk load the index. So these are two different points in the database design space. You can see why text search engines and relational database management systems are separate. Text search engines tune that one SQL query we talked about to death. They really work hard to make that one query they have to service go as fast as possible, and they wouldn't work well for general purpose queries. And so it's sort of a case of engineering for a special case workload versus a general workload. And this is a theme, in fact, that we see across database systems, not just in text search, but many database systems are focused on special case workloads. Even in the relational space, it's often the case that there's not just one relational engine that does everything well. You might use one kind of relational engine for transaction processing, what's called OLTP, online transaction processing. And you might use another engine, or perhaps the same engine but tuned very differently, to do analytic processing, where you're running a lot of big queries. Okay? And there's different kinds of databases also for things like key value storage, where all you're going to do is put and get keys. Examples of that might be MongoDB or Cassandra or Redis. And there's also different databases for things like storing and querying graphs, like Neo4j. And so many database systems focus on special case workloads. It's really not the case that there's just relational databases and text search. Those are probably the two most widely used forms of databases, but there are many other databases as well. And even within relational databases, there are databases that are tuned to particular workloads. So think of text search as a good example in this class of changing our assumptions and as a result, changing our design decisions. And having said that, keep in mind that many of the core issues, indexing, querying, remain the same. And it's useful to learn about more than one of them and then be able to translate, so to speak, from one use case to the next.